Can you see the stream? Are you guys there? All right. Yes, we're here. Okay, great. Thanks. Did the stream automatically show up on the channel? Or did you have to click the link? Okay, so it all right, so you didn't need the link. Okay, great. All right, thanks, Maxwell. And I guess you guys, link was needed. Okay, so maybe we need to change it to listed. All right. So I'll go and I'll make those changes. All right, so I just made it private. I mean, I just made it public, so you ought to be able to get to it. All right. So there's some people who joined the class late, so I better put the link on Canvas here. Also, I'm going to upload the PowerPoint. Bear with me here. So I'm going to edit this later. The last part of this presentation is not complete, but at least I'll throw it up there if you have your workflow or whatever where you like to take notes. All right. So any questions before we get started? Thanks, Matthew. Anything else? Any questions before we get started? Okay then, we will go any questions? Okay, so I don't see any questions. Please note the syllabus. I'll bring it up here for our review. And what I want to draw your attention to is the schedule and where we are today. So this is where we are today, Monday the 14th. We'll cover stress distributions and cross sections and some beam equations. We'll see how far we get with the singularity functions. Probably have to add a supplemental video for that. You should be doing the homework. So you should have done this first, second homework, and you should have identified a team lead, and everybody should have be assigned to a team. Yes, Amanda wants to know, will I go over EES? Yes, I will. So I'll either create a tutorial video or I'll do it as part of the class or maybe at the end of class. Were you guys able to install it? So should have been able to install it. So the test that we're going to have is a week from today, and it's going to cover all of the loading conditions, and we'll give all assigned problems for the test that will essentially be, given this element, this object with these applied loads, what is the stress on a cross section? So, okay, excellent. So that's, I see y'all were able to install, so that's great. Okay, so that's what the test is going to cover. It's essentially a review of statics, and it's going to go through everything that we go through today, and everything that we go through on Wednesday. And it should be similar, the test will be similar to the problems. This part of the class is to make sure that everybody's on the same page with regard to their understanding of statics. Okay, all right. So today we're going to be talking about stresses in cross sections, beams, bending, and deflection. Okay, there's the instructions for EES if you need it. Hopefully you'll be able to get on there. As a recap, if we have a state of stress, the state of stress is actually at a point, and we represent it by this. This is only showing the state of stress on 3 faces. We actually have the state of stress on all 6 faces. And this is the stress tensor that just represents that state of stress. We went over that last time, and we said that there's some orientation where we can resolve these stresses or forces, and that orientation will give us our principal stresses. Okay, this was my write-up of that. This is the eigenvalue problem. This says that, hey, if we have this state of stress, is there a direction such that we have a state of stress that's in that direction, only in that direction? That's what we call our principal stresses. If we solve this eigenvalue problem, which I will not expect you to do on a test, but I do expect you to understand it and know that we get this eigenvalue problem, and when we say that this determinant has to be 0, we can solve for sigma, and sigma will give us 3 roots. This is our stress function, and these real parts of sigma are our principal stresses. They're almost always ordered in terms of sigma 1 is greater than sigma 2, which is greater than sigma 3. The coefficients are shown here, and this is what we showed last time. This is just as a review. And so in the case of when you have a stress strain test, for example, you'll get just sigma x and the axial direction, sigma y and z are 0. And then all of these terms, C2 and C1 are 0. So if you look at this equation, you have a C2. The C2 is equal to sigma x. Then you have a sigma squared times 1 times sigma minus sigma x. And that shows that 2 of the roots are 0. The other principal stress is sigma x. And that's the case of a stress strain test. So even when you have uniaxial stress, the equations still work. The principal stresses we can find as well, and the principal stresses include principal shear stresses. The nomenclature can be a little bit confusing because we have principal stresses. Those principal stresses include the normal stresses and the principal normal stresses and the principal shear stresses. The Mohr circle helps us to draw these and make things a little bit easier. But the entire story is really summed up in this equation right here. Okay, and if we can solve that equation with these coefficients, we'll always know the state of stress in 3 dimensions from anything. If we have plane stress or 2D stress, sigma x and y, then we'll have this. Some people leave this, I think in the book he leaves this as sigma A and sigma B because you always order them as max and min. So if one of them is minus, then sigma 2 would be 0. Sigma 1 would be your max positive stress, and sigma 3 would be your negative stress. And there's a relationship between these principal stresses and the Mohr circle, and if you'll notice, this term here is the same as this term. Okay, and this is your max in-plane shear. It's not necessarily your max shear, and we showed those 3 Mohr circles last time. This is your average stress here, and that's the center of your circle plus your radius. Plus or minus your radius will give you your principal stresses. Okay, and you'll notice that this max in plane is equal to the radius of the circle centered here. All right, so today we're going to be talking about, and if you have any questions, just type it in the chat. I'll try to monitor it and make sure that we don't leave anybody behind. So we're going to talk about a little bit about how stress shows up in cross sections for elements that are used in machines. And one of the simplest states of stress is just our direct shear. And direct shear is just the force over the area. Okay, but in reality, it's almost impossible to have this loading condition because you'll have some gap here, and if you have some gap, then you don't exactly have direct shear, but you also have some moment as well that's going to be applied to that. But this is direct shear. This shows up in pin joints and pin and clevis joints like this. This is a single shear joint. This actually shows up in some machine elements. This could be a bolt or a rivet or whatever, where you have 2 plates that are fastened together, or where you have a rotating joint, or if you have like a crank or cam or whatever, and you don't have room to have a double to have a clevis, then you'll have a single shear, and that's just your force over your area. That's your average shear on that cross-sectional area. If we have twice the area to carry the load, then the shear is half because it's carried by both surfaces, and so that's just shown here. We call this single and we call this double shear. When we have links in pin joints or even in bolted joints where you have them in either tension or compression, where you're transmitting loads through that pin or bolt or joint, then you'll also have something what's called bearing stress. Okay, so the bearing stress is actually the projected area. So it's actually the area, the cross-sectional area that's under there. So this is the length of that pin inside that joint times the diameter. So it's the length times the diameter. So the diameter times the length gives us this area, and we can use that to approximate the bearing stress. And the bearing stress is important because if you have excess bearing stress, instead of shearing the pin, if you have a oversized pin or a bigger pin, then what you're going to do is you're going to crush the area. And so the bearing stress is going to show up here in the link. It'll also show up in the clevis. Okay, and this is not just for this. This is just an example of where we have a pin or bolted joint. Okay, and so the bearing stress is going to show up here on this area of the link, and also on these areas under here of the clevis. Okay, so if we all apply a load, we also have the shear stress, and you can see that that's the orthogonal. Okay, so this is the one, this is the stress that's projected underneath, that's for bearing. And this one is the stress that's on the side. So if you're pulling it, it's the stress that's acted upon by this area, and that's in shear. Okay, and that would be on these shear planes here, or you can see my laser hopefully in the middle, and here. And if that stress is too high, then these will tear out. You'll get a tear out failure. This is a question that was on the PE exam actually. So it's a pretty classical failure mode, and it acts on the shear faces, or it acts in shear on the faces that are orthogonal. So what people will say for a rule of thumb is make sure you have at least the diameter of the pin worth of material over here, so that you can prevent tear out. So this is some pictures from the video from Dr. Norton. He shows us two different types of failure. I do believe, I don't know if these are the same material or not, but you can see in this case we have crushing or bearing failure. And then over here we actually have tear out, and you can actually see the shear plane here. Okay. So that covers a simple case of transverse shear. We also have more complicated cases of how shear stress shows up in beams, and that's due to loading, either transverse loading or bending moments cause transverse shear. Okay, and although we look at the shear here on the face, what we actually have is this shear that is only a state of shear. And remember that the state of shear is actually on a point, but we do abstract it into a little cube. And if we have a shear in this direction, okay, we have to have a shear that opposes that rotational moment, and we have to have an opposite direction there that opposes that force, because the object isn't accelerating, so the sum of forces and moments has to be zero, and in that case we have these elements, but there's also that transverse element. It's just important, I guess, to visualize the shear is actually a shear stress, just like we have shear on the shear on an element. So when things can move, if you can slide, if you apply a load, say here on beams that are stacked, then the shear will actually allow it to slide. But if they're bonded together, then they're prevented from sliding, and then the shear forces in there actually cause warping. Okay, so you will get some warping due to applied loads in beams. Shear warping, it violates our assumption that we have a uniform cross section, but if we assume that the warping is small, which is usually the case for slender beams, which is usually what type of beams that we're using in machine design, then we can still use the shear formula. But as a designer, I think it's very important that there's a caveat. So we can't just use these formulas and think we know the shear, because the caveat is that this is a slender beam. So the question you should ask yourself is, well, what's a slender beam? And where does this formula break down? And it turns out that you can find different shear formulas in different areas for different cross sections, and you can look those up. But for now, we'll use the simplified case and assume we have a slender beam, and you'll promise me that you'll remember that there's a caveat if you don't have a slender beam. So the shear formula can be derived by taking a cross-sectional element from a beam. And in this case, this is a beam that has two different moments applied to it. It's got a distributed load applied to the top, and it's got 2-point loads that are applied, and of course it has reaction loads here. This is a pin joint, so it can't support a moment, and then we have another pin joint here. And so this is just a simply supported beam. And what we can do is actually take this little slice of this beam, and we can say, well, we have to have static equilibrium, and in order for us to have static equilibrium, the sum of the forces have to be 0. And if we have a moment on one side and a slightly different moment on the other side, and we have stress on one side, and we have shear on this plane, and a different state of stress on the other side, then we can say, well, in order for equilibrium to be satisfied and our forces to be 0, well, the stress times the area on one face over here minus the stress times the area on the other face over here minus the shear that's developed along the side of the face in that plane here. Maybe a little bit difficult to see, but it's that shear here, equals 0. Okay, and notice that the shear is multiplied by the thickness of that cross-section T times dx right here. So that's how we get this area that shear acts over. So in order for us to have static equilibrium, that has to be true. We can use the bending stresses, which we haven't derived this yet, but this comes from the Flexure formula, which we'll see later. And then we can group terms and simplify and get an expression for shear that looks like this. And what we do is we simplify this equation, and we take this integral of y dA, and say, well, if we know the distance to the centroid of that plane, that would be this distance from the neutral axis to the centroid of the area above which you're trying to calculate the shear on that plane. We call that Q. And then this becomes the shear formula. Okay? So that's the derivation of the shear formula, and this is where we get it. And there's some caveats here too, and that is that we can calculate the shear stress for different types of cross-section. If we use the shear formula, which is on the previous slide, we're going to get something like this dashed line. Okay, but in reality, the shear stress is actually parabolic. Okay, so it's not exactly this line or this constant value. Over here, we see that, well, if we use this formula and we have a width that's half the height, then this shear formula does a good job. We're only about 3% off. And notice that we're 3% less than the actual value. So if you use this formula, it's actually actually not conservative. It's actually too low. It's actually lower than the real value. If you look at a different type of beam where you have twice the width over the height, then in this case, you're about, at the edges here, you're about 40% different for that shear. Okay? All right. So the shear stress too is not, you can't take like flanges or beams like this and expect it to be the same value. Okay, in this case you have shear stress that's going to jump here and here, and so we just need to be aware of those. The shear formula is not to be used on cross sections that are short or flat. It's not to be used at points of sudden cross-sectional changes, for example, flange to web junction in a wide flange beam. And it's not at a joint on an inclined boundary. And so the point of this class is not to go through all the caveats of all these loading conditions, but to be able to do machine design. But in order to do machine design, it's really important that you kind of understand the different caveats. Okay. This is an example where we have a flange and a beam, and we have a shear which is calculated to be 80 kilonewtons, and you're asked to plot the shear stress distribution. Okay, so what we can do is take the shear stress at different points, points C, B, and B prime, and then calculate the shear distribution at those points. And you can see here that the shear jumps at the transitions between these flanges, and that the max shear is in the middle. Okay, so this just goes through the rest of the calculation. Another thing that's related to the shear is the shear flow, and that's the shear force per unit length along a longitudinal axis of a beam. Okay, so that's this shear that's present, that would be in this axis here on this face. And that shear is important if you're using different types of fasteners. Okay, and you can calculate that as well, and it's important when you're making beams or composite beams or structures or bolted structures, because you are going to have this shear stress that's going to act on these planes where you have either bolted joints or potentially welded joints or nailed joints. In this case we have nails. And so you can use the shear flow calculations, and remember how we had the shear in this face, and we said it had to be counteracted by shear on this face as well. Well, that shear flow is something that we can calculate. This is an example of that. I will not test over the shear flow. It won't be on your test, but I do want you to remember this if you haven't seen it before, or be exposed to it if you haven't seen it before. So in this case, the concept of shear flow helps us design how we need to space the fasteners in this composite joint. And although it may seem intuitive to some people to use this design over this design, it also may not be obvious what is the best design. And so we can pick which one is better. So there was a question from Hal. He says, will we be able to do those calculations on the test? If so, will you go through any problems in detail? So the problems that you really need to know for the tests are the problems on the homework. If I cover something in lecture that was not covered in homework, I'll make it clear that I want you to do that. But in this case, I'm not going to test you over shear flow. I'm more interested to see if you can find the stresses at a cross section from different loading conditions. All right. I hope that answers your question. So then these two cases are compared. In case A, case 1 here, we have a shear of 27 newtons. I think it said that the nails can take 40 newtons, so we're good. And in the second case, we have a shear flow of 83 newtons. And in the first case, we're using the distance to the center here, and then we're using this area above the nail for that shear flow calculation for Q. The Y hat, this is 40, this is 5. Okay, so that's 45. So half of 45 puts us in the middle. So that's 22.5. Okay, and then we multiply the width times the thickness for that area, and we get this Q term here. And then when we plug that in, we can find that it's 27 newtons. And we use the same I for both. Okay. In this case, we're using this area here, this distance, and we're using this area. Okay, so that's 22.5. And then this is times 10 because it's 10. And then times 5. Okay, so it's the distance to the center of that area there. And that gives us a shear that's higher. It's almost twice the value that the fastener. So either you need twice as many nails or you need to change your design. All right, so let's talk about beams. So far we've talked about shear and beams, and we've talked about simple shear, and now we want to talk about stresses developed in cross sections of beams as well. Okay, so when a beam is bent, then we have half the material, well, not half, well, if you have a symmetric beam, the top half is in compression, the bottom half is in tension, as shown here. We use this notation C to be the distance from the neutral axis to the outermost fiber. Sometimes you see the Flexure formula is Y, and Y is just any distance along there, so you can plot Y and get your stress distribution as a function of cross-sectional area. Sometimes you'll see S for beam designers, and it's called the section modulus, and you'll see that like civil engineers and structural engineers will use section moduluses or moduli to design with, and you can actually find those in handbooks for various beam shapes. Okay. The Flexure form, this is the Flexure formula here. Okay, and that's the stress, that's the normal stress on a cross section due to applied moment. Okay, and the sign convention is if you have a smile or you can hold water on the top of the beam, then that's positive. Okay, negative is a frown or if water rolls off the beam. When we have a beam that has subject to an applied moment, it causes a strain in addition to a stress, and that relationship between those two is governed by Hooke's law, and the max strain, which you would expect, is at the top and bottom surfaces. Okay, so this is your stress distribution and this is your strain distribution due to an applied moment. Okay, and this is the stress on a beam from an applied load. The stress anywhere along the beam is just linearly proportional to the max stress that's at the outside of the beam. So the neutral axis is where the resultant force on a cross section is 0. I don't know if it's super useful to memorize that, but it is kind of helpful to visualize that if you have an asymmetric cross section, sort of where the neutral axis is going to be. In the case of a symmetric beam, obviously the neutral axis is in the center of the beam, and we can find it by finding the location where the first moment of a member's cross-sectional area is 0. So that's how that's defined. Usually we just put it in the middle, but if you have a non-uniform cross-section, you may have to find the neutral axis if you can't find it, and this is the method that you use. Okay. So the Flexure formula can be derived simply by looking at the relationship between stress on an element due to an applied moment. Okay, so if we know that the max stress is at the top of the surface and it's linearly related to the bending moment, then we can integrate this y distance from this differential force. If we have this differential force at some height y, okay, we can integrate that over the surface to find the bending stress. And we already found that the stress is linearly proportional to the max stress, and in that case we can substitute for sigma, we can substitute y over c times sigma max, and that allows us to introduce this max distance to the axis from the neutral axis. So then we can find that our max stress is equal to our applied moment times the distance to the outermost surface divided by the moment of inertia. Okay. This is an example. This is definitely something you should be able to do. There's also examples in your book that you should know how to do. And this is just given an applied moment, given a cross-sectional area, calculate your moment of inertia and distances and find your max normal stress on the surface due to an applied moment. Now, if we have a curved beam, then we actually have a different stress distribution. Instead of a linear stress distribution, we have a parabolic stress distribution, and the neutral axis shifts away from the center of the beam, and that's denoted by this epsilon term, and we can find that E term. We can find this distance here by looking at the distance to the center of the circle here, and then subtracting this term here, which is a weighted area over the radius. We don't derive it, but we can summarize the result here, that the inner stress, the stress on the inside surface, sigma I, is given by this formula where we have the applied moment here, and we have this applied moment with this ratio where Ci is the distance from the E, which is the shifted neutral axis, to the bottom. That's Ci over Ri, and that's the distance from the center of curvature to the inside surface. And that's the stress that's on the bottom of the surface, and then we have the outside stress, which is at the top, and this is minus the applied moment over E times A, and that's times C naught, which is the distance from the E axis to the top surface time over the distance from the center of curvature all the way to the outside surface. So stress in curved beams shows up on a lot of elements, such as our arbor press here, which is used to press bearings and shafts, or press things out of press fits. And in this case, we often have an applied load. So this is an example where you have a force-loaded curved beam, and in this case you have this additional force that you need to deal with. If we cut this cross-section right here, the balance of forces is this force is has to be equal to this force, but we also have an applied moment as well to prevent this from moving. So then we can still calculate those same equations with the same geometrical relationships. We just have to add this force due to the applied load on this cross section so that we can find the stress. All right. So it's an important skill to be able to look at a loaded member, and beams show up everywhere because they're pretty much any structural element where you have transverse loads. We can pretty easily find the loads along the beam, and if we can do that, we can find the shear and moment diagrams, and that allows us to also find the deflection of the beam. And so you'll notice that in your project, one of the things that's required is for you to make sure that you don't have excess deflection, I think of 1/1000th of an inch. So you have to make it stiff enough to where it'll hold that position. So we already calculated the shear and bending stresses, so we'll ignore this part. I've added that. So I think too, one of the things I want to mention is when we look at these beam equations, or these try to do the analysis, there's really no magic. We derive the equations by summing forces to zero, and we find reactions by summing forces to zero, and we find our shear and we find our moments by summing things to zero. Okay, so this is a beam subject to 2 point loads, and the question is, what are the reaction forces? This is actually, I think, taken from an FE example. So in this case, we can find the loads by summing forces and moments. We sum forces to zero, we sum moments to zero. If we do that, we can find the reactions at the 2 different locations. And once we get the reaction forces, then we can start to draw the shear diagram. Okay, and the way we draw the shear diagram is we essentially start at a side, and we go over and we slice it. Okay, and so and then we say, well, what does the force have to be on this surface in order to counteract this load condition? Okay, and then we just have this V, which we call our shear, and as we move along the surface, we can cut it each time, and we can see what V actually is. Okay, so in this case, we know RA because we solved our statics problem. Okay, so V is going to be equal to RA until we come over here, and then V is going to be equal to RA minus 1800. Then we're going to come over here, and V is going to be equal to RA minus 1800 minus 900, and then we're going to come up here, and this is going to take us back to zero. And if you look, that's exactly what we get. Okay, so if we slice it anywhere between these 2 point loads, then we have this diagram. Okay, and then we have this diagram that changes as step changes when we have applied loads. Okay, so this is a simple case of applied loads. The sign conventions are here, and I said if you make the beam smile, or it can hold water up here, it's positive. Opposite is negative. And then this is a sign convention for positive shear or negative shear. Okay, and so shear is always associated with a shear on a face. Okay, so if it's trying to rotate the element clockwise, it's positive. If it's trying to rotate the element counterclockwise, it's negative. We can then calculate the moments, because if we know the load on an object, and the moment is the force times the distance, so it turns out that we can take the integral of the shear diagram and get the moment diagram. Another way of doing this is if we sum moments to 0 about a point, then we have the shear at that point, and the further along we go, the higher that moment goes. Okay, and that's what we see here. And so we can do that for each different loading condition at different positions. And so this is more of a manual way to do it. We'll talk about singularity functions, which allow us to just plug and chug, assuming we set up the problem right. This is the overall problem that just shows the different loading conditions. And like I said, this is actually taken right out of the FE, review manual book. Okay. This is another example where we can relate the shear and bending moments by summing forces for different slices and different sections, and then we can add them up. And so you can see here, when we have this 0 to 5 meters, we have these loading conditions, and then we can get the shear. The moment is the shear times the distance plus the applied moment that we get from solving the statics problem to get our loading conditions at the ends. And then we can get it from the next section from 5 to 10, and then we capture the entire loading conditions. And you can see that this is a constant. If you integrate a constant, you get a line. And then here, this is a line. And if you integrate a line, you get a quadratic. Okay. When you have a distributed load, the change in shear per unit displacement is equal to the applied load at that point, or the area under that distributed load. The change in shear is equal to the area under the distributed load. And this was taken from some of my sketches, so sorry if it's hard to see, but these are your graphical methods of doing that. For your moment diagram, if you sum your moments about an element, and this is this element here, where we have a moment here and a shear plus a change in shear, and then we have a moment plus a change in moment. All this says is that for an element with two sides, that these are not necessarily equal. And if we have a distributed load here, then we can calculate that. And this allows us to sum the moments. If we sum the moments, we include the shear and change in shear terms and the distributed load terms, and then we can find that the change in moment is equal to the integral of the shear. Okay, and that's what I had showed you graphically as well. For concentrated loads, we have the same equations where we are just taking an element and we're representing arbitrarily all of the loading conditions. And here, if we have an applied moment and a concentrated force, the change in shear is equal to that force, and the change in moment is equal to the applied moment. Okay, so the change in shear, the change in shear is equal to the applied force. Okay, so here we see that goes down by 1800. and then comes over here and drops down again. So all you have to do is find your reaction forces and then slice and then go. Note that when you have an inflection point, you have a change in direction of the shear. Okay, so this goes from positive slope to negative slope. When you have that, you have a change in direction here. And then here you have a step change, which you go from negative to more negative. This is another example where you can calculate these by integration. The relationship's really just pretty simple, though. Here's another example from the FE study guide with a distributed load that you can work out on your own. Here's another example. This is from I believe it's from the Hibbler Mechanics of Materials book. And it shows how to do this if we have a point load, distributed load, and a moment. All right. So now we're going to talk about deflection. And so when we design machines, often a constraint is that the machine's frame or base or element cannot deflect more than a certain amount. And we can determine what this is by looking at the beam's elastic curve, and that's the deflection that passes through the centroid of the cross section of the beam. Okay. We've already talked about the sign convention. What's interesting to note here is the relationship between the moment diagram and the elastic curve. Okay, so you see here we have a change in direction because we have a change in direction in the moment. And so you should be able to look at a moment diagram and you should be able to say, oh, okay, well, I kind of know what's happening with the deflection of my beam. At this point where the moment diagram crosses through zero, we have an inflection point, okay, and that's when the slope starts to go change from negative back up to positive. And then up here we have a maximum, okay, and at the maximum and minimum of the moment diagrams we have a max and a min in the elastic curve, okay. So this is another example with the moment diagram and the elastic curve. This is how we can derive this relationship. So if we look at a tiny little segment here of the beam, and we look at how that segment changes in geometry before after an applied bending moment, we actually get a strain. And that strain is going to be at the beginning we have this element's distance is ds, and then after we apply load, that distance changes slightly. If it's above the neutral axis, it's being compressed in this case, which makes it smaller. So we can say that this is our radius of curvature rho, okay? And if we have rho, which would be like the radius times d theta, that's the angle, it's the distance that the arc traces out, right? So if we have ds, which is dx, that's rho d theta, where this is the curvature and then this is the angle that it goes through, and that's dx. ds prime, which is the smashed version, okay, it's going to be rho, which is the distance to the neutral axis, minus y, which puts us right here, times d theta, and that gives us dx. Okay, so then we can call this term epsilon, which is rho minus y d theta minus rho d theta over rho d theta, or pull out the rho and say 1 over rho is equal to minus epsilon over y, where epsilon is defined as the strain. And then we can use Hooke's law, where we have the stress is equal to the strain times Young's modulus. And then we can plug that into the Flexure formula, which we know that if we have an applied moment, we get a bending stress. And if we put that bending stress in this equation, where we have Hooke's law, and then we plug that into this curvature equation, then we get this relationship now between the bending and deflection of a beam. Okay, and this is how we can describe the elastic curve. Now, there's a kinematic relationship between the radius of curvature and the location x. Okay, so this is our curvature equation from calculus. And if we use this and we assume that this term here is really small, this is actually our deflection term, then we can say that, well, this is 1 over rho is approximately equal to d squared v over dx squared, and this is our displacement. Okay, so that allows us to then use this equation and replace the 1 over rho with this deflection. Okay, and then that allows us to then have a relationship between an applied moment or a moment at a beam's cross section and its deflection. Okay, and what's beautiful about these equations is we already know that the moment is the derivative of the shear, which is the derivative of the distributed load. And if we divide these right-hand sides by EI, then we just have these equations which we can integrate and take the derivative of, and we can find the deflection. Okay, so for the elastic curve, then if we have this slope of the beam, and we say, well, the tangent of this beam is this little amount dv over dx. Okay, and if we say, well, if theta is really, really small, and we know that the tangent of theta is the sine over the cosine, and if we have really, really small theta, we can say, well, if the sine of theta is approximately theta, if theta is really, really small, then the cosine of theta is about 1, so then the tangent of theta is about theta, so then we can say, oh, well, the slope of the curve is actually dv dx, okay, the change in y over the change in x, and that's the slope for our beam. Okay, and so we can use that relationship, and we can take the integral, and then we can impose boundary conditions from different joints on those equations, and we can integrate and solve for those loads. So here's the procedure to get your elastic curve, load and moment functions, and then the slope of your curve. Okay, so what we can do is use those loading equations that are here, okay, for shear, distributed load, and moment. And in this case, this is our moment equation. Okay, so we say this is our moment, and then we can introduce these terms, which come by equating it equal to m, and then we can integrate that, and then integrate it again, and every time we integrate it, we need to keep our constants of integrations, and then we can use a boundary conditions. So this boundary condition says that the slope is equal to 0 at x equal to L, and that the displacement is 0 at x equals to L. Okay, so that means over here at this base, the slope and the displacement are 0, and so we can plug those in and solve for the slope and the deflection of the beam. That's this deflection VA here. Okay, and then we can put in the numbers and actually calculate the slope and the deflection. In this case, the slope is at A, which is at the tip of the beam, this theta A. It's 0.0164 radians. And then this deflection here is about 2 inches for this beam of length L. Okay. This is another example of finding the max deflection due to a distributed load. And in this case, all we have to do is take half the beam and analyze it, and then get an expression for the load in terms of x for the moment. Once we get the moment equation, we can set it equal to our elastic curve equation, and then introduce this displacement. And this dv dx is the slope, and then v is the actual deflection. And we can just integrate that and then plug in our boundary conditions and solve for coefficients, and then find the expression for the slope as a function of this displacement. And in this case, this is what it is. I'm going to we'll stop here for today a little bit early because I don't have these slides sorted out just yet. I will say one thing though. This is some simply supported beams we can use for superposition. So I have some more stuff in here, but I don't have this yet organized. I think I'll cover the. Sorry, I'm going back and forth. I hope I'm not making you sick on your screen. But I think what we'll do is we'll cover the singularity functions and how we can use those to represent different loading conditions instead of using the integration. So for now, we have this method which works, okay, where we can introduce, based upon the moment equation, the elastic curve and solve for the deflection and slope. I'm going to show you how to do this also with the singularity functions, which I will show you in the next lecture. So I'll stop here. I think I will mention one more thing though. We talk about beams. The cases that we covered, I would say, are undergraduate in the sense that we don't have enough time to get into all the details. But for beams, there's also statically indeterminate beams, okay, that we will commonly encounter in real machines. They're obviously all over the place, like bridges. And for statically indeterminate beams where you have an over-constrained systems, then you can find which supports are redundant and then remove them and then find the reactions and then use equilibrium to reintroduce them. Another thing you can do is use superposition to find deflections, and then from different loads you can remove them and then add them back. We may or may not get into this. And then the last thing that I have on here is when you have a asymmetric bending. Okay, so if you have a non-uniform cross section, how do you deal with that? And you deal with that by finding the location where you have your principal axis of inertia. Okay, and there's methods for this. At this point, I'm just mentioning it to you because you need to know that if you do not have uniform cross sections, then you're going to have to do a little bit more work to find your loading conditions for bending. Okay. The other caveat is if you have composite beams or beams made from different structures or cross-sectional areas that change, you also have to account for those. And there's a way to do that. We can still use the flexural formula, but we have to light transform the beam into an equivalent beam made from the same material. And so that's a trick that you can use to do that. This is the procedure for this example. This is an example of how to do that, but this is not something that I'm going to test you on. So I will go back over the singularity functions for our next class. And I think what I just want to mention is that we do have asymmetrical asymmetrical cross sections and composite beams that you need to be aware of. So at this point, I want to ask if there are any questions. And we'll just leave it open here for a minute. If there's no questions, feel free to drop off, and I will see you on Wednesday.